It is the autumn of 1942, somewhere on the Eastern Front, and a German ordnance sergeant named Wilhelm Kessler is kneeling in the mud beside an American Studebaker truck that his unit captured 3 days ago outside Riveted. The truck smells of diesel and wet canvas, and something else, something clean and almost chemical, like fresh machined metal. Kessler is not here to drive the truck. He is here because his commanding officer handed him a written order that morning, and the order said to document everything. Every marking, every plate, every stenciled number inside the cab. The Wehrmacht had been capturing American vehicles in increasing numbers since the Lend-Lease convoys began pushing material through Iran and Murmansk, and someone at the Ordnance Inspectorate in Berlin had noticed a pattern that nobody could quite explain yet. Kessler pries open the engine compartment cover and holds his lantern up to the instruction plate riveted to the inside panel. It is a small thing, pressed steel, 4 inches by 6 inches, the paint slightly chipped at the lower corner. The text is in English, which Kessler reads badly, but the numbers he can read fine. He copies them into his notebook. Then he moves to the second plate bolted inside the cab door, then a third on the firewall. Then he begins to cross-reference. He stops writing. He looks at the plates again. Then he looks at the engine components. Then he walks to the second captured Studebaker parked 20 meters away, takes a wrench from his kit, removes a fuel pump, walks back and bolts it onto the first truck. It fits. First try. No filing, no adjustment. He stands in the mud for a long moment looking at his hands. What he has just understood, what he will write in his report that night, in language that his superiors will find either remarkable or deeply alarming, is not about this truck. It is not even about American trucks. It is about something that happened in a government armory in Massachusetts more than 100 years before the war began, and about a doctrine so thoroughly embedded in American industry by 1942 that the men who built the truck had never once stopped to think about it. They had simply done it the only way they knew. The question Kessler's reports will eventually put to Berlin is this: how does a country build that into everything, all at once, across 10,000 factories, without ever issuing a single order telling them to? Nobody in Berlin had a satisfying answer. Part 1. The answer that changed everything. In the summer of 1851, a man named Elisha King Root walked through the Crystal Palace exhibition in London and watched British engineers crowd around a display case containing 15 American Colt revolvers. The British engineers were not admiring the revolvers, they were testing them. They had disassembled all 15 guns, mixed all the parts together in a heap, then randomly selected components and tried to reassemble working pistols. Every pistol worked, every time, without filing, without fitting, without a skilled gunsmith standing over the bench making adjustments. Root was Colt's chief engineer. He watched the British engineers and understood exactly what they were reacting to. They were reacting to something that had no name yet in European manufacturing, a thing the Americans had been building toward for 40 years, starting in the government armories of Springfield, Massachusetts and Harper's Ferry, Virginia. The thing had a name by then, though barely. Some called it the American System of Manufactures. Some called it interchangeable parts. The British engineers at the Crystal Palace called it, with a mixture of admiration and unease, the American method. Hold that phrase, it matters. The American method was not a single invention. It was a doctrine, a philosophy of production built on one foundational idea, that a part should be defined entirely by its dimensions, not by the skill of the man who made it. If you could hold a part to a precise enough tolerance, you could make 10,000 copies of it, and they would all fit the same hole. You would not need a craftsman to fit each part to its neighbor. You would need a machine, a gauge, and a worker who could read a number. The man most responsible for turning this idea into industrial reality was not a famous name. His name was John Hall. 58 years old by the time his method was fully mature. Born in Portland, Maine, trained as a gunsmith and engineer, he He spent the better part of 3 decades at the Harper's Ferry Armory perfecting a system of gauges and machine tools so precise that parts made on different machines in different shops by different workers would fit each other without adjustment. When the Army tested his rifles in 1826 by disassembling 100 of them, mixing all the parts, and reassembling them at random, every rifle worked. Think about what that required. Every hole drilled to the same depth, every thread cut to the same pitch, every surface ground to the same flatness. Not approximately, exactly. The gauges Hall designed were themselves the standard physical objects that embodied the dimension against which every part was measured before it left the machine. If the gauge said no, the part was scrapped. Not adjusted, scrapped. This was the brutal logic at the heart of the American method, and it ran directly counter to the European craft tradition. In European manufacturing, and German manufacturing in particular, the skilled craftsman was the standard. He measured with his eye, his hands, his accumulated judgment. He fit a part to its neighbor with a file and a whetstone and 30 years of experience. The result was often beautiful, often precise, but it was not interchangeable. When the craftsman's work broke, you needed another craftsman to fix it. Stop and think about that distinction. It is not a small one. It is the entire war. By the 1880s, the American method had moved out of the armories and into the civilian economy. Singer sewing machines, McCormick reapers, Pope bicycles, every one of them built on the principle that parts are defined by dimensions, not by the man who makes them. And in every case, the same downstream consequence followed. You could ship spare parts. You could train a non-specialist to make repairs. You could maintain a machine 10,000 miles from the factory that built it with nothing but a parts catalogue and a wrench. When Henry Ford opened the Highland Park plant in 1913 and began assembling the Model T on a moving line, he was not inventing a new principle. He was taking the American method to its logical conclusion. If parts are truly interchangeable, then assembly itself can be mechanized. You do not need a skilled assembler to fit each component to its neighbor. You need a worker who can perform one specific motion, over and over, because every part he receives will be identical to the last one. Ford's line produced a Model T every 93 minutes by 1914. The previous record, at any factory in the world, was roughly 12 hours per vehicle. Hold that number. The German automotive industry of the 1930s was, by most measures, technically excellent. Mercedes-Benz, BMW, MAN, these were companies with superb engineers producing machines of genuine sophistication. But they were building in the European tradition. Their tolerances were tight where it mattered and loose where the craftsman's judgment said loose was fine. Their parts were often specific to the individual vehicle they had been fitted to. Their repair manuals frequently called for fitting, a word that meant a skilled mechanic would take a new part and adjust it until it matched the old one. This was not a deficiency of German engineering skill, it was a different philosophy. The Germans were optimizing for quality at the individual unit level. The Americans were optimizing for something different, scale. And in 1939, the question of which philosophy was correct became the most important engineering question in the world. Part 2. What the Wehrmacht ran on and what it couldn't. In September of 1939, the Wehrmacht invaded Poland with approximately 300,000 motorized vehicles. By June of 1941, the figure had grown to around 600,000. By the end of 1942, after 2 years of continuous campaigning in conditions that destroyed vehicles at a rate no one in the German planning staff had seriously modelled, the maintenance situation was, in the word used by Colonel Rudolf Schreiber of the Army's Motor Transport Inspection Branch, catastrophic. Schreiber wrote this in a report dated November of 1942. He was 44 years old, a career logistics officer from Munich who had spent the interwar years studying Soviet industrial capacity and had tried, repeatedly, to get someone in the Army's upper echelons to take seriously the question of how Germany would maintain its vehicle fleet in a prolonged war. No one had listened. Now he was writing the word catastrophic in a report that would eventually reach the desk of Albert Speer, and he was doing his best to explain why. The core problem was not production. Germany could build trucks. The core problem was interchangeability, or rather, the lack of it. The Wehrmacht's vehicle fleet in 1942 comprised somewhere between 120 and 150 distinct vehicle types. Not models, types. Different manufacturers, different specifications, different parts, different tolerances. A carburetor from an Opel Blitz would not fit an Einheits LKW. A wheel bearing from a Mercedes-Benz L3000 would not fit a Magirus Deutz. A fuel pump from one Krupp truck would not fit another Krupp truck of the same nominal model if the two vehicles had been built in different production runs, because the craftsmen on the floor had made slightly different decisions with their files. Schreiber's report contained a table. The table listed 47 common failure modes across the Wehrmacht's truck fleet. For 31 of those 47 failure modes, the repair required either a part sourced from the original manufacturer or a part fabricated on site by a qualified machinist. Only 16 of the 47 could be repaired with a part pulled from a general supply depot without some form of fitting. Read that again. 16 out of 47. 34%. 2/3 of all common breakdowns required either a factory part or a skilled tradesman to fix. In the middle of Russia, in November, with the nearest factory 4,000 kilometers away. Now consider what this meant in practice. A truck breaks down on the road to Stalingrad. The axle shaft has sheared, a common failure on the rutted Soviet roads that were not roads at all, but frozen mud tracks with rocks in them. The field workshop has a replacement shaft, but the replacement shaft is from a vehicle that was built 3 months later than the broken truck, and the flange dimensions are 2 mm different, and the bolt pattern does not quite match. The machinist in the field workshop can make it work. He is a good machinist, trained in Stuttgart. He knows what he is doing, but it takes him 6 hours. 6 hours for one truck. There are 40 trucks waiting behind it. This was not a hypothetical. Schreiber documented exactly this scenario, with different parts, in 11 separate instances in his November report. In one case, a convoy of 22 trucks trying to reach a forward supply point near Rzhev in October of 1942, 17 of the 22 trucks broke down en route. 11 were repaired in the field. 6 had to be abandoned because the parts needed either did not exist in the supply chain or could not be made to fit without equipment the field workshop did not have. The cargo, ammunition and rations was distributed among the 11 surviving trucks, which then completed the journey 3 days late. 3 days. For a supply convoy carrying ammunition to men in contact with the enemy. Now meet the truck on the other side of the equation. The Studebaker US-6 was built in South Bend, Indiana, starting in 1941. It was a 2.5-ton 6x6, meaning 6 wheels, 6 of them driven, with a Hercules JXD engine producing 95 horsepower, a 5-speed gearbox, and a 2-speed transfer case. It weighed 4.5 tons empty. It could carry 2.5 tons of cargo on the road, more across country. It had a top speed of about 72 km per hour on a good surface and could operate, not just move, but operate at temperatures as low as -40 Celsius. Studebaker built 197,000 of these trucks between 1941 and 1945. Most of them went to the Soviet Union under Lend-Lease. The Soviets called it the Studer. Red Army drivers called it the best truck in the war, which is a statement that deserves scrutiny, given that they had access to every truck in the war. But the number of trucks built is not the important number. The important number is this. Every single one of those 197,000 trucks was built to the same specification. Every bolt, every bearing, every seal, every gasket, every shaft. Every part in every truck was interchangeable with the corresponding part in every other truck. Every part fits every. The plate riveted to the interior wall of the cab was not advertising copy. It was a technical statement. It was the American method, stamped in metal, riveted to a vehicle that was about to be driven across the most punishing terrain in the world by men who were not mechanics, maintained by workshops that might be 300 kilometers from the nearest supply depot, in conditions that would destroy any lesser system in weeks. The German ordnance sergeant in the cab with his flashlight understood that he was looking at something important. What he could not yet articulate, what would take the German ordnance establishment the rest of the war to fully understand, was that the plate was not describing a truck, it was describing a system, and the system was the weapon. Here is the key detail that almost every account of Lend-Lease misses. By German standards of individual vehicle quality, the US-6 was a competent but unremarkable piece of engineering. Its engine was not the most powerful, its suspension was not the most refined, its cab was not comfortable. There were German trucks that were faster, there were German trucks with better payload ratios, there were German trucks with more sophisticated drivetrains. None of those German trucks could be repaired in a field workshop in 20 minutes with a part pulled from a crate that had been shipped from Indiana 4 months ago and had been sitting in a Red Army supply depot since then, and have the repair work correctly the first time, every time, without a skilled machinist touching it. The Studebaker could. If the front axle failed, you replace the front axle. If the gearbox failed, you replace the gearbox. If the engine failed, the whole engine, you dropped in a new one, and it fit, and it ran, and you were back on the road. The Red Army's maintenance manuals for the US-6 specified repair times for common failures. Axle shaft replacement, 45 minutes with 2 men. Gearbox replacement, 2 hours with 2 men. Engine replacement, 4 hours with 3 men. These times assumed no fitting, no adjustment, no machinist's judgment. They assumed that the part in the crate was identical to the part in the truck, because it was. Because that was the specification. Because that was what those 4 words meant. Now multiply that by 197,000 trucks. The Germans were not blind to this. The Ordnance inspection reports that began filtering back from the Eastern Front in late 1941 and through 1942 contain a consistent thread of something that reads, in the careful language of military bureaucracy, very much like alarm. A report from the Army Group South Ordnance Section, dated March of 1942, noted that captured American vehicles showed a degree of parts standardization not observed in comparable German production. A follow-up report from June of the same year, after German forces had captured larger numbers of Lend-Lease vehicles, used a more specific word: systematic. The American standardization was not accidental, the report noted. It was systematic. It was designed. It was the point. The report recommended that Germany investigate whether similar standardization could be applied to Wehrmacht vehicle production. The recommendation went up the chain, it was discussed, it was studied, and it ran directly into a wall that had nothing to do with engineering. The wall was the German industrial structure itself. Part 3. Why Germany couldn't copy what it saw. In the spring of 1943, Albert Speer, 37 years old, architect turned armaments minister, running on coffee and ambition and the growing certainty that Germany was losing, convened a conference in Berlin to address the Wehrmacht's maintenance crisis. Among the attendees was a man named Dr. Heinrich Kniepkamp, 49, chief engineer at the Army Weapons Office, responsible, among other things, for vehicle standardization. Kniepkamp had read the ordnance reports from the Eastern Front. He had read Schreiber's November report. He had, by this point, a fairly precise understanding of the gap between American and German parts standardization. He presented his findings at the conference. The numbers were not encouraging. The Wehrmacht's truck fleet, Kniepkamp reported, required approximately 56,000 distinct spare parts to maintain. The American military's truck fleet, larger in absolute numbers, operating across more theaters, required approximately 16,000. The ratio was 3.5 to 1. For every part the Americans needed to stock, the Germans needed 3.5. For every warehouse the Americans needed to maintain their supply chain, the Germans needed 3.5. For every parts clerk, every inventory record, every shipping manifest, every depot shelf, 3.5 times as much, for an army that was already stretched. Stop and count that yourself. 56,000 parts, for trucks, not for tanks, not for aircraft, not for artillery, just trucks. Kneepkamp's recommendation was what you would expect: consolidate, reduce the number of vehicle types, force manufacturers to adopt common specifications, standardize bearings, seals, gaskets, fasteners across the entire fleet. It was, in essence, a proposal to impose the American method on German truck production, retroactively, in the middle of a war. The proposal died in committee. Not because it was wrong, because of what implementing it would have required. To standardize parts across the Wehrmacht's truck fleet in 1943, you would have had to shut down production lines, retool factories, redesign components, and retrain workers, all simultaneously while the factories were also being bombed by the RAF and the USAAF, and while the front lines were demanding more trucks, not fewer, not later, now. The lead time for retooling a major production line was 12 to 18 months in peacetime. In wartime, with bombed-out machine shops and disrupted supply chains, it was longer. More fundamentally, the German manufacturers did not want to standardize. Standardization meant giving up the proprietary parts that gave each manufacturer a captive repair market. An Opel truck needed Opel parts. A Mercedes truck needed Mercedes parts. This was not an accident, it was a business model. And in the 1930s, when the Wehrmacht was being built up and the manufacturers were being handed contracts, no one in the procurement system had the leverage or the inclination to force them to give it up. The Americans had solved this problem differently. Not better, necessarily, differently. The American solution had started with the government armories in the early 1800s, where the government owned the tooling, set the specifications, and had no interest in proprietary parts markets, because there was no parts market. When the system moved into civilian industry, it moved through a competitive market that selected for interchangeability, because interchangeability was what consumers wanted. A sewing machine you could get parts for anywhere, a bicycle that a local mechanic could fix. By the time the American automobile industry standardized on the Society of Automotive Engineers specifications in the 1910s and 20s, the culture of interchangeability was already embedded in American manufacturing. The SAE standards, bolt sizes, thread pitches, bearing dimensions, were not imposed by the government. They were agreed by manufacturers who understood that a common standard grew the market for everyone. Germany had SAE equivalents. The Deutsches Institut für Normung, the German Standards Institute, known as DIN, had been publishing standards since 1917. DIN standards covered bolt sizes, thread pitches, bearing dimensions, everything the SAE covered. The problem was not the existence of standards. The problem was that the Wehrmacht's procurement system had not enforced them. Each manufacturer had been allowed to deviate where its engineers thought deviation was justified, and over 15 years of military vehicle procurement, those deviations had accumulated into 56,000 distinct spare parts. By 1943, it was too late to unwind them. Here is the most brutal irony of this entire story. Germany's manufacturing culture, its pride in craft, its tolerance for individual variation, its faith in the skilled machinist's judgment, was genuinely excellent at producing individual items of high quality. The German truck that a skilled mechanic could keep running was often, truck for truck, a more capable vehicle than its American equivalent. Better payload per ton, better engine efficiency, better off-road geometry in some configurations. But war is not a competition between individual vehicles. War is a competition between systems. And the American system, the one that produced a truck every few minutes on a moving line in South Bend, Indiana, stamped a plate to the interior wall saying every part fits every, and shipped it to a Red Army driver who would maintain it with a parts catalogue and a wrench in the middle of a Russian winter. That system was not competing with the German truck. It was competing with the German system. And the German system was losing. had been losing in this particular dimension since 1851, when British engineers at the Crystal Palace mixed up the parts of 15 Colt revolvers and found that they all went back together. The mid-roll break here feels almost indecent, but the people who built these trucks, the engineers at Studebaker in South Bend, the ordnance officers who wrote the specifications, the workers on the line who held the tolerances, they deserve a moment of recognition. They were not soldiers. Most of them would never get closer to combat than a newsreel. But what they built, and the precision with which they built it, kept armies moving on the other side of the world. If this investigation is giving you a clearer picture of how the American industrial system actually worked, not the version that survives in the victory narratives, but the version that a German ordnance sergeant documented in a notebook in the winter of 1942, press the like button. It keeps this kind of history visible a little longer, and that matters. Part 4. The Forensic Verdict. Let us be precise about what the German ordnance establishment actually understood and when, and what they did about it. The first systematic German analysis of American vehicle standardization appears in the records of the Army Weapons Office in the autumn of 1941. It is a short document, 4 pages, and it is primarily concerned with technical specifications, engine displacement, payload capacity, ground clearance. The mention of part standardization is almost an aside. The analyst notes it as a feature of American production philosophy without drawing operational conclusions. By the summer of 1942, the documents have changed in character. The ordnance reports from the Eastern Front are no longer primarily concerned with technical specifications. They are concerned with operational consequences. The language has shifted from descriptive to diagnostic. Words like systematic and doctrine appear. The analysts are no longer just cataloguing what the Americans built, they are trying to understand why it works. The November 1942 Schreiber report is the clearest statement of the problem, because Schreiber was a logistics officer, not an engineer. He was not interested in how the American trucks were built. He was interested in what happened when they broke. And what he documented, with the precision of a man who had spent 20 years counting things, was that American trucks, when they broke, were fixed faster, with fewer skilled workers, using parts that came from a depot rather than a factory, and returned to service at a rate that German trucks did not match. He calculated a figure he called Verfügbarkeitsquote, availability rate, the percentage of a vehicle fleet that was operational at any given time. For the Wehrmacht's truck fleet on the Eastern Front in October of 1942, Schreiber calculated the availability rate at 51%. Roughly half the trucks the Wehrmacht had in Russia were running at any given moment. The other half were broken down, awaiting parts, awaiting skilled repair, or awaiting evacuation to a rear area workshop. He did not have direct access to Soviet figures, but he had access to something almost as useful: captured Red Army logistics documents. From these, he estimated the availability rate for Lend-Lease American trucks in Soviet service at approximately 78%. 78 against 51. If you have 100 trucks and 78 of them are running, you can move 78 loads. If you have 100 trucks and 51 are running, you can move 51 loads. The Germans had more trucks on the Eastern Front than the Soviets for most of 1942. They were still moving less cargo. Think about what that means. Schreiber's report was not the end of the German analysis. It was the beginning of a more uncomfortable one. Because once you understood the availability problem, you had to understand why it existed. And once you understood why it existed, you had to confront a conclusion the German military planners had been avoiding since the beginning of the war. The conclusion was this: Germany had gone to war with a logistics system designed for a short conflict. The Blitzkrieg model, fast, deep, decisive, had been explicitly designed to avoid the kind of attritional logistics war that Germany had lost in 1918. The Wehrmacht was not supposed to be maintaining 150 vehicle types across 4,000 kilometers of front for 3 years. It was supposed to be in Moscow by October of 1941 and dictating terms by Christmas. When that did not happen, the Wehrmacht found itself fighting a war its logistics system was not designed to fight. against an opponent whose logistics system was specifically designed for exactly that war. The Soviet Union, in the 1930s, had made a strategic decision to acquire American manufacturing technology and American manufacturing methods. The Ford plant at Gorky, built in 1932 with American technical assistance, produced vehicles on American tooling to American specifications. The Ural Truck Factory, the ZIS plant in Moscow, all of them built with significant American technical input, all of them operating in the tradition of the American method. When Lend-Lease began delivering American vehicles directly, they were entering a maintenance system that already understood American standardization, because Soviet industry had been learning from it for a decade. The Germans were not facing just American trucks. They were facing an entire industrial philosophy that had been building toward this moment for 140 years, since John Hall started making interchangeable rifle parts in a government armory in Virginia. Now look at what happened after the war. Rudolf Schreiber survived. He spent the post-war years working for the West German Bundeswehr's logistics planning office, where he wrote a series of internal papers on vehicle standardization that drew heavily on his wartime analysis. He died in Munich in 1971 at the age of 73. His November 42 report was declassified and studied by NATO logistics planners in the 1950s, and portions of it influenced the NATO standardization agreements, STANAGs, that governed Allied vehicle parts interoperability through the Cold War. The problem he documented in The Mud of the Eastern Front became a foundational case study in military logistics doctrine. Heinrich Kniepkamp also survived. He was interrogated by American Ordnance officers after the war extensively about German vehicle development. The transcripts of those interrogations are in the National Archives. He was remarkably candid. Asked about the parts standardization problem, he said, and this is documented, that the Wehrmacht's vehicle fleet was a maintenance officer's nightmare, and that the American approach to standardization was the correct one from a logistics standpoint, which we understood too late and could not implement in time. Too late. Could not implement in time. Those 6 words are the forensic verdict of this investigation. The US-6 carried no remarkable armament, no exceptional armor, no revolutionary propulsion system. It was not a wonder weapon, and it was not technologically advanced. What it had was a plate riveted to the interior wall of the cab, stamped with 4 words that represented 140 years of American industrial philosophy. 4 words. Every part fits every. The plate was not bragging, it was a promise, and the promise was kept 197,000 times across the Russian steppe, through mud and snow and 40 below cold, maintained by drivers who were not mechanics, repaired by workshops that were hundreds of kilometers from the nearest factory, kept running by a logistics system that worked because it was designed to work at scale, in the worst conditions imaginable, without craftsmen. A German ordnance sergeant sitting in the cab that winter night in 1942 wrote those 4 words down 3 times. He knew he was looking at something important. He was right. He was looking at the thing that was going to win the war. Not the truck, the system. And here is what that means, stated as precisely as possible. Wars are not won by the best individual weapon. They are not won by the bravest soldiers or the most gifted generals, though those things matter. Wars at industrial scale are won by the side that can keep more of its equipment running, more of its soldiers supplied, more of its logistics chain intact, under the worst conditions for the longest time. The side that can do that wins. Not always quickly, not always cleanly, but it wins. The American industrial system, descended from John Hall's gauges and Elisha Root's factory floors and Henry Ford's moving line, was not built for war, it was built for commerce. It was built because interchangeable parts were profitable, because standardization grew markets, because a sewing machine you could get parts for anywhere sold better than one you couldn't. The military applications were a consequence of a philosophy that had been selected for by the market over a century and a half. Germany's manufacturing culture was also selected for by its market, a market that rewarded individual quality, craft skill, and proprietary systems. It produced magnificent things. It produced the Mercedes-Benz L3000 and the Panther tank and the Junkers Jumo engine. It produced things that German engineers were, with justification, proud of. It produced 56,000 spare parts for trucks. That ordnance sergeant climbed down from the cab of the Studebaker eventually. He finished his notebook entry. He probably wrote a report. The report probably went into a file. The file probably went to a desk in Berlin where someone read it and understood it and could not do anything about it, because the system that would have needed to change had been building for 30 years and could not be rebuilt in the middle of a war. He was standing in the dark, in the mud, in Russia, with a flashlight and a notebook, looking at 4 words that told him everything about why his side was going to lose. 4 words on a riveted plate. Every part fits every. He had read it correctly the first time. He just hadn't known what it meant. By the time Germany did, by the time Schreiber's report and Kniepkamp's analysis and 100 other documents had assembled the full picture, the Studebakers were already rolling east, and the Red Army was already moving, and the supply lines that kept them moving were already working, part fitting part, every time, exactly as specified, exactly as promised, exactly as stamped on that plate. The most important engineering document of the Second World War was not a blueprint for a tank or a schematic for a bomb. It was a small metal plate riveted to the inside of a truck cab with 4 words on it, and it meant what it said.